The Digital Equipment Computer User Society presents this live recording from the 1985 Spring DECUS U.S. Symposium, held May 27th through the 31st. We take you to New Orleans, Louisiana, where the program is just now beginning. The following material is for informational purposes only, and is subject to change without notice. Neither DEC, the author, nor DECUS assume any responsibility for the material, its use, or applications.
Last meeting, this is there we go. Bill Hunter. He's the product manager for communications and networks for the Personal Computer Systems Group. This is the Rainbow Communications technical session, and Bill will first give us a short overview, and then he will accept questions. And when you present your questions, please say first your name, then your affiliation, and if you have more than two questions, please just ask the first two and then go to the back of the line. Thank you.
Okay, what I'd like to do in this session is to give a brief, a technical overview of the communications capabilities on the Rainbow. We'll be basically oriented towards programmers in this session. We're going to cover the capabilities of the basic Rainbow system, extended communications option, and the operating system support that's available for programmers.
Any chance of getting your slides afterwards?
If you give me a business card, I can get hard copies run off and mailed out to you.
Thanks very much.
Okay. Everything that's in this, I believe, is pretty much available in the technical documentation set also. Okay, the basic communications ports can handle protocols that are designed to use asynchronous lines, bisynchronous lines, and also it can handle the HDLC and SDLC protocols. The port can handle internally generated clock speeds from 50 to 19.2 kilobits in asynchronous mode. In the synchronous modes, typically the clocking would be provided from a modem or another external source. The internal clock generators are separate for the transmitter and receiver, so that if split-speed operation was necessary, that could be used. There is a loopback point for diagnostic use, when that loopback takes place between the outputs of the 7201 and the RS-232 or 423 drivers and receivers. Okay. It has a range of character sets that can be used with this port, from 5 to 8-bit characters. You can use even, odd, or no parity. And error checking can take the place of, can take one of three forms. Either a vertical redundancy check, which is typically just using parity, a longitudinal redundancy check, which I believe is typically an XOR of essentially all of the characters in a message with the results tacked onto the end. It's a little bit more powerful than the vertical redundancy check. And finally, a cyclical redundancy check is supported. This is probably the best type of error detection. Is typically used in the synchronous protocols, the bisync, SDLC, and HDLC. The CRC functionally you can just think of the entire message as one large bit stream that is in turn divided by another large binary number, typically expressed as a polynomial. The quotient is thrown away and the remainder is tacked on to the end of the message. And on the receiving side, the process is handled the same way, and then the results compared. There are two major types of CRCs floating around today. There's the CRC-16 and the CRC-CCITT, and the port supports both of those polynomials. Standard-wise, the port conforms to RS-232 in the functional realm. The electrical interface has the speed and distance characteristics of RS-423. Modem controls, there are primary and secondary signals. Among the secondary signals we support are the secondary received line signal detect, secondary request to send, and we also support speed select and speed indicator. The port's composed of one half of an NEC 7201, and that chip is also shared with the printer port. The base port uses channel A, the printer port uses channel B. Okay. Some address assignments. The communications control and status register basically contains the bits to allow you to set the modem signals and to read the status of modem signals. Clock generator, that register is basically divided into two halves so that you can set the transmit and receiver clock rates independently. Clock source, it's basically one bit in that register to determine whether the clocking should be supplied from the onboard generators or from an external source such as a modem. The rest of that register is actually used to set the printer bit rate. So you've got to use a little care when you're setting that bit. You've got to find out what's in that register first. And we have a slight mistake here. I'm not sure exactly where the problem is, but the 7201 channel A is used for data and control and status, not channel B. So either the port number is incorrect or that should read A for both of those. Sorry, I'm not sure which one it is. That information is in the technical documentation set, but I'd be glad to look it up when I get back if anybody's in need of that.
It's on the 8088.
It's on the 8088. Yeah. All the communications is run from the 8088. Okay. The interrupt vector address for that port is 90 in hex, which did not make it to the slide. The printer port is basically pretty similar to the COM port. We're really looking to do the same thing, to get a bunch of bits out over a serial line. There are some differences. It is implemented as data communications equipment, so that the printer to the printer port would look sort of like a terminal does to a modem, which means we have a few signals reversed. Data terminal ready and send data, in this case, are actually used as input lines to the 7201. Receive data is the output line. And we have data set ready and clear to send always asserted. The other major difference between the standard port is that the speed of the printer port only goes to 9600 baud. Extended communications option. There are two ports. The asynchronous and synchronous modes are the same as for the standard communications port. It means we can also support the synchronous data link control and HDLC protocols. There is DMA support into a 64 kilobyte address space down at the bottom of memory. Again, this allows you to relieve the CPU from processing character interrupts with every byte that goes in and out of the system. The DMA support on this board has independent channels for the receiver and transmitter of both ports. So we have 4 DMA channels on there. Same hardware as on the standard port, the NEC 7201 for the communications, and the Intel 8237 DMA controller. And the interrupt vector addresses are as shown here. Port A, the port without a home. Not much I can say about that. We had a use for the port when the board was originally conceived. It was going to be used to drive the infamous external Winchester, which never appeared when we figured out how to put one inside the box. If anyone has a use for RS-422 communications at 721 kilohertz, it's there for you to use. There's a 9-pin connector on the end, and it uses balanced data and clock lines. That is 2 lines for the data and 2 lines for the clock. Port B is probably the primary port for that board at this point. It's a superset of the base communications port. I mentioned the DMA capability that it has. It also has the ability to generate a clock signal and feed it out on one of the clock lines. It's known as the DTE transmit clock, and it can be used in a configuration where you might want to attach a couple of rainbows back to back using synchronous communications in a modem-less environment, or to connect to some relatively cheap modems that do not provide a clock for the transmitting station. We've added a circuitry to actually detect an idle line as defined by HDLC and SDLC, and also to generate it. This is something which apparently in most situations is not absolutely necessary to work with those protocols, but we felt that at some point we ought to be at least consistent with them, so we put that circuitry in there. Also, there is a circuit in there which will kick in an internal clock in the event that the external clock goes away at the end of a received message. We've run into the situations where there are some modems out in the world today that can be strapped so that the modem will stop supplying received clock data once it senses a loss of carrier. And in a synchronous environment where you're doing CRCs, especially with this type of a chip where the CRC calculation is delayed, if you lose the clock, you can't finish the CRC calculation. So this will kick in a clock at some very high frequency, just enough to get the chip through the calculation. Address assignments for this port. Communications control and status register. Again, that's the same type of information as is in the base port. A register where you can clear any DMA interrupts. Register to reset the entire operation of the option, and separate data and command status registers for each channel of the 7201. Here are the address assignments for the DMA controller. They'll be available afterwards. You can copy them off my slides if you want. Most of them are read and write, with a few that we've saved for other uses. Okay, that's about the end of the hardware overview. On to the operating system support. We will provide support for asynchronous communications. If you want synchronous, you're totally on your own on that one. We have identical support for the standard communications port, the printer port, as much as possible given its implementation as a DCE, and the extended communications option port B. Okay. The protocol support is indeed primitive, and the support can be accessed through several mechanisms. There is a task level interface using pretty much standard get and put type of calls. There's a provision to supply user exits to the interrupt service routines from the operating system. And finally, if you want to do it all, or most of it yourself, you can tell us where your interrupt service routines are and what interrupts you want to handle. And we will give those to you. We'll process the others ourselves. In the areas of protocol support, the basic system assumes no protocol. It does give you the facility to tell it to use an X-on or an X-off protocol. And with the modem signals that are available, you could implement your own type of request to send, clear to send protocols, or one which might depend on DTR being on or off. The multiple interface levels, again, the task level. All these interface levels are really implemented in the extended BIOS as far as actually getting at them to set things up. You have get and put type of routines at the task level and routines to read and set the modem status, where you really need minimal control over the system. At the user exit level, we will dispatch to your routine after a character has been read and the interrupt serviced, or after we've serviced a transmitter empty interrupt, but before we've actually written the character out onto the line. And again, the device interrupt level, where you can write your own interrupt service routine and just tell us which ones you want to handle. Task level interface contains the same support for the MS-DOS operating systems, CP/M, and concurrent CP/M. You can either use our 30-byte buffer, or we recommend that you supply your own buffer to use with this. There are control calls, I/O, and status calls associated with these. As far as the control calls go at the task level, you can ask that the 7201 be reprogrammed either to specific characteristics and settings that you want, or that the settings that are found in NVM as a result of the last setup operation can be used. You can clear the received character buffer at any time you wish. You can set modem signals or check the modem status, and there are provisions to start and stop a break. There's no call to, say, put a break out on the line for 3 or 4 seconds. We've decided to leave the timing up to you because of the limited clock facilities in the Rainbow. Input-output calls. We have both pended and immediate calls to get and put a character. And the pended calls will wait until the event has happened. And on the immediate calls, if there is no received character available or the transmitter buffer is full, we will return status to you. There is also the capability of getting a character placed at the front of the transmit queue. If you are running an X-on, X-off type of protocol, and we're running with a relatively small buffer, you might want to get the flow control character out on the line immediately to cut down the chances of missing any characters. Status calls, these are basically pretty self-explanatory. You can read the setup for the device, find out what the input and output status is, and read the status of the modem signals. On to the interrupt service routine level interface. They're user exit oriented. You tell us where your routine is to handle the transmit characters and receive characters, and after we get them in and do preliminary servicing of the interrupt, we will give control to you to perform any processing you want. This offers selective control. You can handle just the receive or just the transmit, or both. Calls allow you to set or reset the invocation of your routines for the transmitter or receiver, or you can use it to gain control over status change interrupts. And finally, at the device level, you're the boss. Tell us where your ISR is, what interrupts you want to handle, and we'll give it to you. That concludes the formal presentation, so I'll take any questions that you have at this point. Hopefully I can answer some of them too. It's been a while.
Jim Wilson from the Rochester Institute of Technology. We have an application where we have to do some interrupt handling. And when we started reading through the technical documentation, we found that there were some discrepancies and called telephone support and worked through the local DECUS. And we have a minimum of 3 different interrupt vectors documented for all of the different ports. Where do we find out which one is in fact the actual one? I mean, you listed 90 in hex for the standard COM port. Is that, in fact, the exact interrupt vector?
I hope so. I have a hard time sometimes relating to the documentation here, because that technical documentation set went through a couple of iterations. One potential source of confusion might have been when MS-DOS was put out on the Rainbow. At the time I was deeply involved in those details, it was before MS-DOS was even thought of. I do recall that there were some hiccups around the time we decided to put MS-DOS out, because some of our interrupt vectors were in conflict with MS-DOS's software interrupt vectors. So there may be some problems in and around that area which may result in some of that confusion. My best suggestion would be to, have you talked to Bruce Gibson in the Rainbow support at all?
No, so far all of our questions have been directed to the local DECUS. We haven't gone to, other than to the telephone support, we haven't gone to anyone directly in DEC yet.
Well, I can get answers to those things.
Yeah, I'd very much like some information, because we are having trouble writing this routine. And my second question is related, similar to a question that was brought up in the last section with that SAMNA problem, and that is, once writing your own interrupt routines, upon exiting, can you properly restore the environment so that you can continue as a standard MS-DOS Rainbow operating system, or do you in fact have to reboot?
You should be able to reset things so that you can continue on.
Okay, we've had some trouble with that. We've tried doing some interrupt service routines and then restoring back to the original vectors at the exit, and it's not doing quite what we think it should be. And have had to reboot the system when we finish the user-written program.
Okay. First I've heard about it.
We did find something documented in the technical reference manual indicating that it looks like you cannot restore the initial environment, that you do have to reboot. But we weren't really quite sure if we were reading that right.
That sounds strange to me. The only thing I can suggest is that if you see me afterwards, we get your card, and we can get you in touch with the right people who can answer that question.
Okay, thank you.
Bill Rich, Scientific Atlanta. You were saying that these get character testing for pending and modem status and all that, that's in the BIOS. Is that documented in the BIOS manual, in the listings and all that?
It would, I believe, probably be in the listings.
Both BIOSes, CPM and MS-DOS?
Yeah, if they're current listings.
Okay. And the second part is, for MS-DOS, do you have a device, an extended communications device driver that would support, for instance, setting the baud rate, detecting if a character was ready, and things like that are not supported on the COM port in standard MS-DOS?
Yes. Yes, that's using the same support.
I mean, do you have an additional device driver that will run, that we could load?
No.
No, I don't think so.
Bob Riley, Dickinson College. I was wondering if it's possible to implement the mini exchange hardware product off of the printer port of the Rainbow, given its limitations.
No. I believe that has to do with the fact that the printer port is configured as a DCE. Yes, and the mini exchange is always expecting to be the DCE. So
no tricks or anything there that we could try to play to make that work. It'd be very nice use of the mini exchange if we could actually hook it up to the printer port.
Yeah, we looked at that. I think we pretty much determined that there were some hardware reasons why we couldn't do it. They escaped me at the moment, but I believe there were some signals that were always asserted or that were missing. So we decided we could not do that. Okay. I know they do some magic in the mini exchange to allow it to connect to a modem, because they're both DCEs. They have a magic connector cable that you use.
Gene LaRue, Eastern Connecticut State University. In writing a communications program, in CPM, is it the only way that you can communicate by clearing the interrupts
I'm not sure I understand.
Okay, in writing a communications program like that, the only way that I found to be able to get access to another, like Rainbow, if you're communicating together, is to clear the interrupts as soon as you start. Is that the only way that you know of, or is there somewhere other than that?
I'm afraid I still don't quite follow.
If you write a communications program to communicate, let's say, two rainbows
Right.
under CPM,
Okay.
now the only way you can get them to communicate is by clearing the interrupts to be able to communicate back and forth.
You mean they transmit and receive interrupts as they happen?
Yes. Now, is that the only way about going about that, or is there?
No, one could write it to use a polling method, if you wanted, where you basically don't use interrupts, but you constantly look at the status on the chips for receiving, for characters available, or transmitter buffer empty. That's.
But what I found is, if you don't clear the interrupts to start with, you will not be able to send out a character. Let's say I'm trying to send out a character. It just won't get through.
Oh, you're in the initial setup.
Yes.
You mean? Oh, okay. It's probably always advisable to do that.
Okay.
Anyway.
I was just wondering if there was another way around doing that, or.
No, I think you'd want to.
Oh.
Anyway.
Thank you.
Ken Harris from Unico. I have a comment about the interrupt vectors for the communications port. I have experience with the extended communications port, and under MS-DOS there's a conflict with the interrupt vectors that MS-DOS uses, and the hardware vectors have been relocated to different places, and there's additional confusion because it makes a difference whether you have an A or B. They've been relocated to different places on the different machines. So if you have an A, at least on the extended communications port, and the DMA controller for the extended communications port, that the documentation that you get with the COM port is wrong. Those aren't the addresses they give you for the vectors are not correct. And it's a different location for the whole set of vectors depending on whether you have an A or a B. And I think that's correct in the current version of the MS-DOS technical doc set.
Okay, thank you. I should have caught that. I was working with the information that was a couple of years old. Yes? It is correct. Okay. If it isn't, that's the documentation follower, and you can slit his throat. One comment which Dave Gallagher brought up to me after the last meeting in reference to the question on the SAMNA and its problems. Dave's told me that there is a patch that has been written to cure SAMNA of its characteristic of letting your system go blowing away out into the wilderness if you want to use the communications line after it's been running. We'll try and work on getting that patch made available as a standalone patch. Currently, I guess it just ships, it's bundled with the Rainbow Office Workstation, but we'll do what we can to try and get that patch made available, possibly through the, I don't know, DECUS library or something like that. Anyone else?
Okay, I would like to take this time to announce that the PC-SIG is running a clinic tonight, 5 to 8 p.m., room 2206 in the Hilton. And I would like to thank Bill Hunter for the presentation of this session.
This is the end of this cassette. Please rewind this cassette for the next playing.